This is a lesson on acceleration in the kinematics unit. It follows after definitions for motion, for position and displacement, speed and velocity. Acceleration is the rate change of the velocity vector. Notice that it is a vector. A vector has magnitude or direction, therefore the velocity vector may change in magnitude or it may change in direction. These are two separate types of acceleration. The first we call a linear acceleration, and the second one may result in circular motion. That's not linear, right? So these are two different types. But when we look at the definition of acceleration, we can say it is the change in the velocity vector over the change in time. And that's the average acceleration. The velocity may have changed in different ways between the two initial and final points, but all we care about is the velocity at the initial point and the velocity at the final point. This is very strict on that, just like average velocity, average acceleration, just cares about the final and the initial. This is a vector quantity, again, and the units on it, SI units, is meters per second squared. Notice that we're going to take velocity, which has units of meters per second, and divide by another factor of time, and that's how we get time squared down there. Instantaneous acceleration is a very similar concept to instantaneous velocity. Instantaneous means at a particular instance. So you may accelerate in different rates across a period of time, and we can ask about the particular value at different instances in that time period. If you know calculus and the velocity function as a function of time, you can take the derivative and find the acceleration, which is a very useful mathematical tool. But in the algebra-based sequence, we do not tackle that. To practice acceleration vectors, which can be tricky. It's very tricky because there's a difference between acceleration and deceleration. Often deceleration is associated with a negative sign with the acceleration, but acceleration is a vector, which means that the coordinate system is very important. And what I'm going to do is assign a coordinate system up here and say plus x is to the right. Okay, so what I have for us is an activity that looks at the sign of the acceleration as opposed to the type of motion that happens. And this motion, if we're accelerating, we could be speeding up or we could be slowing down. And that is pretty explanatory, right? If my velocity is increasing in value, I'm speeding up. If I'm going faster, I'm speeding up. If I'm going slower, I'm slowing down. My velocity would decrease in magnitude if I'm going slower. Okay, so this is a fun activity. We're going to do vectors here. Plus 2, we know to be in the plus 2 direction, positive x. I'm going to make the plus 5 longer than the plus 2. I'm going to look at the difference between these two vectors, right? Because acceleration is the change in the velocity over the change in time. So let's look at the change in velocity. The final velocity is a plus 5. The initial velocity is a plus 2, and I'm subtracting it. So I'm going to draw it in the other direction. So you can see that the change in velocity vector is in the positive direction, which makes sense. I increased speed, right? I increased so I'm speeding up from 2 to 5. My acceleration says that it points in the same direction as both of the original vector and as in the final one. Okay, and in my coordinate system, I note that this vector is pointing to the right, so it gets a positive sign. And this is sort of makes us happy that the speeding up has a positive sign. It's speeding up. Let's look at a slowing down one. I'm originally traveling at 6 meters per second, slow down to 1 meters per second. So let's do v final minus v initial. I definitely slowed down, right? I can write this slowing down I can write that out here before knowing any of this, that it slowed down, right? So V final is a +1. V initial, I'm subtracting it, so I have to go -6. And so the acceleration, the change in velocity, is a -5. Do you see that? -5. And so the sign of the acceleration is negative, and we can see that it slowed down. Okay. Again, pretty satisfied. That makes sense with how we think about velocity out in the world and acceleration. All right, let's look at this. We're moving -1, and then later, at some later time, we're moving at -3. And when I think about that, when I go from -1 to -3, 3 is a larger speed. So in this situation, we can fill out this last column and say that it's speeding up. This thing is definitely speeding up. Let's do the vectors here. I have a -1, and then it increases to a -3. I'm going to do V final minus V initial. So V final is -3. V initial is the negative of -1. And so the change in velocity was a -2 over whatever time, right? So when I think about the acceleration vector is this -2 kind of represented there. And it's pointing in the negative direction. Notice that the sign of the acceleration comes from the coordinate system, and it's negative. So now you may be a little bit unhappy because it's speeding up and I have a negative sign. You say, Sarah, doesn't negative acceleration imply that it's slowing down? And you can see that it depends on the velocity vector. If the acceleration vector is in the same direction as the velocity vector, it's going to speed up. And that's what we saw in the original picture, right? These two velocity vectors are in the same direction. It's speeding up. These two vectors are in the same direction. The acceleration is in the same direction as the initial velocity. You're going to see speeding up. As opposed to slowing down, you see that in here? The original velocity vector was to the right. The acceleration vector was to the left. They're opposing one another, and that's slowing down. Let's do the last row, and hopefully this is coming together for you. What we're going to see is that we have a -7, and then at some point later it's -4. We can see that vector got smaller, so I know it's slowing down. Okay. Let's draw the vectors. The final velocity vector is -4. The initial velocity vector was a -7, so I subtract -7 and I end up adding 7. And so the acceleration vector turns out to be this, in the same direction as, in the positive direction. And again, we're seeing this sort of maybe different than what you expect, that I get a positive acceleration vector because it's pointing in the positive direction in my coordinate system, but it corresponds to slowing down. So that's what you watch out for, is this object increasing in magnitude of its velocity vector or decreasing in magnitude of the velocity vector? And whether it's slowing down or speeding up will depend on the orientation of the initial velocity vector and the acceleration. If it's speeding up, those are the blue. If it's speeding up, those two vectors are in the same direction. If it's slowing down, that's in the red. Those two vectors are opposing one another. So watch out for that. Negative acceleration doesn't always mean slowing down. You have to ask yourself, what's the direction of the velocity vector? That will tell you definitively. This is the velocity versus time graph. I just created a velocity versus time graph. When you look at the axes here, the horizontal axis is t in seconds. The vertical axis is velocity in meters per second. And we can maybe even go through and identify points on here. Let's see, I have 1, 0. This is 4 seconds, 9. This one is a little bit later. This is 9, 9. And this one's way down the road. This is 27, comma 0. So those are our 4 points at the edges of our three different regions. So what it's asking us, it says for the motion in the graph below, determine the acceleration for each region. So I'm going to create a row for each region, 3. And the definition of acceleration is up here. We take v final minus v initial and divide it by the time elapsed. So the acceleration for region 1, I went from 0 meters per second to 9 meters per second. So I get 9 plus 9 minus 0 over 3 seconds from 4 to 1, right? 4 to 1, the time difference. So I get plus 3 meters per second squared, meters per second per second. So that's the acceleration there. You may have an idea of the second region. It starts at 9 meters per second and ends at 9 meters per second. So whatever the delta time is down on the bottom, it's irrelevant. It's at 0 meters per second squared. It's not accelerating. It did not change speed. There's no acceleration there. It's just a flat line. For the third region, we can do the change in position over the change in time. The change in position, the final position is 0, and the initial position is 9. So 0 minus 9 on top, and we get 27 minus 9 on the bottom. So I get negative 9 over positive 18, and that will give me a negative 0.5 meters per second squared. And I have that negative in there. You can see that corresponds to the slope. The sign of that slope is negative. This is a positive slope, positive 3. You can see that this is a higher magnitude. This is a not as steep slope, so I'll have a smaller value overall. Draw a graph of the acceleration versus time. We can see that there's time here and acceleration here, and we have our different time periods, 4 seconds, 9 seconds, 27 seconds. So let's line this up. We know our values for acceleration. From 1 to 4, the acceleration is 3. I can just draw that in here. From 1 second to 4 seconds, the acceleration is 3. From 4 seconds to 9 seconds, during that 5-second time interval, it's 0. So I will just write across here a line at 0. It's fine that I have a line on 0, and that represents the acceleration during that time. There is a velocity. The velocity is not 0, but the velocity is not changing, so that corresponds to an acceleration of 0. For the last 18 seconds that we're concerned with, the acceleration is negative 0.5, so I can draw that in here. Negative 0.5. Notice it's below 0, and it extends across here. Negative 0.5. And that'll be the acceleration graph versus time. A related question here is it asks to write an equation for the velocity as a function of time for each region. Oh, interesting. The velocity as a function of time for each region. Okay. So the equation, the velocity as a function of time, well, that's the initial velocity plus the acceleration, whatever was gained due to the acceleration. And this will be the general form that we use as a function of time. So if we know initial velocity and acceleration and a period, the time expression, we can figure out the equation for this actual line. And if it were me, I would do region 2 first. Region 2 seems to have the easiest line. The velocity of region 2 as a function of time is 9. It is a constant value throughout that period, and that's it. And this will be for the time period from 4 to 9. Let's work on the other two regions. The velocity for region 1. The initial velocity for this one is 0. It starts at 0 velocity. The acceleration we decided was 3 meters per second squared. And we need an initial term because it doesn't start at 0. So I'm going to put a plus 3 here, and then I'll say t minus 1. I start 1 second less. So then I can simplify this. This equation simplifies to -3 plus 3t. So if I back this up to the x-intercept, it's a -3. And that's why that is how it is. Okay. I would accept either one of these. This is technically the simplified version, but this would be perfectly fine as well. V3 as a function of time, you may be getting the hang of this. The initial velocity here is 9. We slowed down. We calculated this on the previous slide at 0.5 meters per second squared. And the time here is 9. T minus 9, right? So when I simplify this, we get 9 minus 0.5 t plus half of 9 is 4.5. So overall, this will give us 13.5 minus 0.5 t. And that would be the equation of velocity versus time, or velocity as a function of time in that third time period over here. That equation. If we drew all the way back here, the x-intercept or the y-intercept would be 13.5, and that's why that is what it is. It has a negative slope. We expect that, as opposed to the positive slope in region 1.